start by saying this is work with Mathieu Fetch from Toulouse University and Pascal Louis from Tours. And the first part of the talk will be embarrassing for me to tell, because Betty Lone is in the audience, and I learned so much from her papers about this, far beyond what I'm saying here, because this is pretty standard, but I want to start slowly, and I want also to insist on my motivations while I do this. So my apologies to all the experts in the audience. So let's do something which is mathematics of about at least 70 years ago. So we are working over a field K. Everything here will be over a field, so nothing lost if I'm working over the complex numbers. It will be equally interesting. And let's study a finite dimensional K algebra. And everything here will have a very finite dimensional flavor, in a sense which I will make more concrete. And deforming such an algebra in infinitesimally means that I'm looking for a new multiplication over the dual numbers, and I want to find a new multiplication which reproduces the old multiplication plus a new term I'm interested in. So I'm looking for MAB, and the important point is that the multiplication should stay associative, and that translates into an equation, and of course you can work out the equation easily. And it is an equation for m. Here I'm writing the old multiplication plus m triple a b is equal to m triple a b c plus m triple b c. And I take a couple of very trivial lessons. So first of all, associativity is an equation. I've worked over the dual numbers, and an equation which was nonlinear has become a linear equation. That's the first observation. And
missing the C and A.
I'm missing here things which I should miss.
External multiplication.
The external multiplication is missing here and here. Sorry, yeah. And now the insight I want to keep here is that insight one is that this is interpreted as m twiddle is a 2 cocycle in a complex, which is the bullshit complex, and this has co-chain groups, which are linear forms from A tensor n into A, and it has differentials, and I'm writing the differentials in a graphical notation. So if I have a linear home which goes from A3 into A, then this is done by taking the linear home, multiplying here, then subtracting a term which uses multiplication, then writing down again with a term with positive sign, negative sign, and finally again a boundary term, and we will see these pictures in a moment again. So the second insight is that I should say, if you want to check that this is a differential, you use associativity.
It's a differential of something with 4 inputs, right?
Sorry?
The D of something with 4 inputs gives you that.
A D applied to something with 3 inputs gives you something which has 4 inputs. That's why I'm writing it in this way.
Sorry, you're correct.
Yeah, and the second insight is that low-dimensional cohomologies gives you well-known expressions. So, for example, you get the center, you get differentials, and in second cohomology cohomology. You get deformations of multiplications. And a third insight we want to keep for later is the following one, that there is a generalization. So if I'm taking here as the output, not necessarily A itself, but if I replace this by an A bimodule, and I say that here I'm multiplying with A from the left, or I'm multiplying with A from the right, then I can write down Hochschild cohomology with coefficients. So I get Hochschild cohomology with coefficients. And what is the benefit of having these coefficients? Well, that's quite a lot. You can relate Hochschild cohomology to X. And we will do a similar thing for Davydov-Yetter cohomology, which hasn't been done before. Looking at the relation between bimodules and vector spaces, you can write Hochschild cohomology as a bar complex, which is big, but conceptually lies. And another thing which I want to emphasize is that in these coefficients you get long exact sequences, which are of course a very nice tool to compute. Yeah. Of course, to many people in the audience, this is something you've seen probably dozens of times in this seminar. Yeah. So now I want to do a similar thing, and I want to deform associators. So maybe I should say a few words what I really want to deform. So if you look at representation categories, so for example, representations of a Lie algebra, representations of a group, say of a finite group, and these are not just categories, but these are monoidal categories. So they come with a tensor product. You can form the tensor product of two representations of a group. And now it's not just about forming a tensor product of two objects in your categories, but the tensor product should be associative. So associative could mean that you are requiring two objects with independent bracketing to be the same. Well, then asking two objects in a category to be the same is always wrong. So you can ask them to be isomorphic, and then you introduce additional data. This is the associator. Now, what is the reason for imposing associativity? The reason is that any rebracketing should give the same result. That's how we should define associativity, and then you prove a combinatorial theorem that it's enough to require this for 3 terms, and that's the associativity. At least our generation learned in high school. I'm not so sure about the present day high schools in Germany. Yeah. So now, what is the thing you want to have now? For different rebracketings, you get isomorphisms. So no matter how you go from one bracketing to the other one, you get an isomorphism by using this data. But if you do this in different ways, it shouldn't matter. It should be the same isomorphism. Now, for example, here in this diagram, you can go from this bracketing to this bracketing by using the appropriate associators. And now you want to have that any two of these paths give the same isomorphism. And it's a combinatorial question to work out what is necessary to impose. And the statement is it's necessary to impose this identity. So for example, I have to see whether I did this correctly, but let me take this that I'm not wasting time here. Here, for example, you would rebracket using alpha, u, v, and deal with w, x as a single object, and you can fill in the other associators. Good. This is a pentagon. This is what we want to preserve in order to have the same isomorphism between different expressions coming from different bracketings. And the importance is this is an equation between associators. It is nonlinear, and this is what you impose to have a tensor category. And now we want to play a similar game. So we want to take our associator and we want to start here with some associator A, take the dual numbers and look for associators of this form. Again, having in mind that this linearizes, this leads us from a nonlinear equation to a linear equation. So it's literally the same way to do this. And this is only one of the problems. Another related problem is if you have a monoidal functor. What is a monoidal functor? Well, if a monoid is if a monoidal category is a monoid in the world of categories, then a monoidal functor between two monoidal categories is the same as a morphism of algebra. And again, we don't want these things to be the same, but you need here some structure morphisms FU2, and they obey some non-linear equation. You can linearize it, and you can work this out. And I should mention that these monoidal functors are extremely interesting because you can capture a lot of structure, at least we find interesting in terms of monoidal functors. So, for example, crucial for our applications is the notion of a module category. So if a monoidal category is a monoid in the world of categories, this is a module in the world of categories. There's some mixed associators, again, pentagons, which you can linearize. And you can capture this in terms of a monoidal functor from C into the end of functors. This is nothing else than what you know from the description of modules. And it's also interesting to deform gradings. Well, what is a grading? A grading can be described in terms of a monoidal structure on the functor, which I call P. This is a linear product for the experts, but don't mind, which takes two objects and simply tensors them. And if you ask what is a monoidal structure on this functor, then you have to compare P x1, y1, tensor P x2, y2 with P of the tensor product of these two. So xy tensor y1 tensor with x1 box times y2. And if you write down what this is, here I'm tensoring, so I'm getting x1, y1. I'm not writing all tensor products now. x2, y2 on this side, and on this side I get x1 tensored with x1, y1 tensored with y2, and you see the crucial things that you have to exchange these two. So a grading does the job. Conversely, if you investigated monoidal structures up to some small garbage, give you gradings. Yeah, so that's why we want also to deform monoidal functors. And I promised that I would say a few words on why we started to address the problem. So my main interest is two-dimensional conformal field theories, and in two-dimensional conformal field theories, there has been a lot of mathematical work. So there is a notion of what their symmetries should be, vertex operator algebras, but maybe you don't want to have the definition. What you want to have is that they have representation categories, which are monoidal categories. They have a lot more structure. They are actually so-called modular categories. They are graded. The grading has properties, and I'm not going to go into these details. And then you have to specify another datum, which is a module category over C. And it's not just a module category, but it has additional data, like it has to have traces and this stuff. In any case, we have this datum. And the mixed associators we have for the pentagon in the module category have a very direct interpretation. They are OPEs of boundary fields, whatever this is. So if we can deform them, we can deform physically interesting theories, and we want to understand how does it work. And I should be completely honest and say we are at a present stage of technology which we have. We are not able to address this because there is additional structure which we don't have under control, the deformation theory setup. But this was our way to get into the subject. So, and we have to learn more, and hopefully, since we will have an expert on this type of things in Hamburg soon, we will make progress in this respect by some more help. And let me also make the general remark that in this field there is a kind of a dichotomy. There is so originally people specified here to the case where C is semi-simple. So if we are in a morally semi-simple world, also for this, then there are no deformations. So there is some rigidity, which in the field goes under the name of Opniano rigidity. And in my talk, I will sketch you how to get conceptually such a rigidity result that you do not have deformations. Yeah, and then of course in the non-semi-simple case you want to understand the deformations. You want to know how many of them are there. Can you compute it? That's the program. And now I want to give you a certain flavor of this. And
something?
Yeah.
So I know you don't want to give the definition, but can you give some sense of what is an object in this rep?
This is a representation over a certain vertex algebra. So you fix a vertex algebra, which you can think about roughly as a commutative algebra with some differential. Now you start to study modules over them. This is a bit more subtle than I'm saying, because very much like Lie algebras have too many representations. You have to be very careful what category to specify. This is work that has been done by other people. So there are nice categories of representations where you know that they are monoidal, that they are braided, and you know quite a bit more. And these are the categories we have in mind. But then we use the power of category theory, and we forget that they are so complicated. And we work with them as categories with certain properties. That's the power of abstraction, if you want. Yeah. Question? Okay, I understood the position of your hand in the wrong way. Sorry. So okay. Good. So now, of course, writing down here the linearization of this equation, identifying that it's a complex. That's what many people in this audience could do within one afternoon, and it has been done. It has been done by Davydov and Yetter, and I think both would insist that these were two papers. By no overlap over the authors, both would insist very strongly. Okay. So still, the community puts it together into Davydov-Yetter complexes, and I should tell you what we want to do. And I make a few simplifying assumptions. C and D are monoidal categories, and I want them to be actually finite tensor categories, which means that they have finiteness properties. They are equivalent as abelian categories to categories of finite dimensional modules over a finite dimensional algebra that makes certain objects to exist without going to int objects and this stuff. But generalizations are obviously you can envisage. And quite importantly, the tensor product is rigid. So every object has a left and a right dual, and the tensor product is exact. This is not true for all vertex algebras, but this is how we can make some progress. And of course, there should be generalizations, which we don't understand at the moment. So the definition of the Davydov-Yetter complex is the following one. You define it for a monoidal functor. And the complex has as co-chain groups, it has natural transformations. So, and it has natural transformations where I take here f acting on n copies of the tensor category, and then I tensor together, and the various ways to write it down. Actually, I take here natural endotransformations. So these are endotransformations of a function from C tensor n to B tensor n by F tensor n, and then I tensor everything together. So yeah, B tensor n, and then I tensor everything together to D. Yeah. So the code chain, and we will see more than this complex in an hour. So this is actually, if you one column in a complex, Violetta might show, but only the kernels in this row. Yeah. So, but just to put these two talks into context. And now, if I take a natural transformation, characterizing by their components, this should be something which takes something which has n inputs up to fxn and extends it to something which has one more input. Then you get terms here up to fx1 to fxn. And now you start to get the following pattern. Now I take here an input which is x0 tensor x1. Here I have x2, and you should see here I'm doing tensor products instead of the products of an associative algebra I did before. And this goes with plus and minus signs, and obviously ends with something which is of the form that here a line of fxn ends. Now I want to find the coefficients. How should I do this? Yeah, coefficients for the advantages I described, and these coefficients were not known before. So let me change perspective. The following perspective is very useful. If you have two monoidal categories, then the categories of functors, and I mean here linear functors, these are all linear categories, is a monoidal category. It is a monoidal category by a convolution product, which is called day convolution, prime day. It's not related to any night. Yeah, so, and this convolution product is something you can write down explicitly. So the new functor is given by a certain coend, and C1 tensor C2 into C. It's a coend over C1 and C2, and I'm taking the two functors here. And I don't want to bother you with too many details here. For some people here, this is something you know. For some people, this is new. But the observation is that if you take a monoid in this category here, it is just a lax monoidal function. So this is the first thing we use. So let me notice, and let me say how it goes on. If we know that the functor is a monoid in this monoid category, we can follow the Hochschild pattern, right? So this wasn't the way we discovered it, because usually you discover things in a more complicated setup, but this is the way we now understand it. And I should say I learned this from discussions with Ross Tweed. So this is not our insight, but the coefficients were first, that we got this insight, and now I use this insight to introduce the coefficients to you in a simpler way. Yeah, just to give full credit to Ross Tweed, in case Ross Tweed.
I have a question about the differential.
Yeah.
So you go from small to CN plus 1, and then I understand the first term, but I don't think I understand the middle term.
The second here.
Yeah, you compose.
I take here
objects.
I take here the tensor product.
Yeah.
And then I go on with the fxn, And upstairs
Yeah,
here.
where do you get upstairs?
Yeah.
How do you split it again?
Let me just get my notes. I was too quick.
Actually, the first and last term, shouldn't you have just one output?
No. I'm splitting them by not splitting them. I take the tensor product of x0, x1, then fx2, and so on.
Yeah.
Okay.
But then the x0, x1 are not.
And this is x0 tensor x1.
As an output.
Fx0 tensor x1.
Yeah.
Fx2.
Yes. Yeah. Okay.
And I have to check that this is a differential that needs properties of this, namely
F.
I need properties of f, and f obeys some equation because it's a monoidal functor. That's the point where I'm using that it's a monoidal functor to show that the differential squares to 0.
Okay.
It's an exercise that needs paper.
Okay.
Yeah.
Okay.
Okay, good. And to show that what I had here, that let me just see, to show that observation 1, that f in the functor category from C to D is monoidal, and I should write here lax monoidal, and for the experts will know what I mean, is equivalent to f being a monoid. Being a monoid needs some piece of structure. Multiplication is exactly the lax monoidal structure. Yeah. So, and then I can compute, I can observe that, first let's observe that Davydov-Yetter cohomology is just the same as Hochschild cohomology, internal in the monoidal category of functors from C to D monoidal with day convolution. Of course, this means unpacking day convolution, checking that it gives this equation, and this is nothing I'm going to do in the blackboard. But if you're happy with this statement, then it is clear that we should also know what are coefficients. So the coefficients should be f bimodules. And what is f bimodule? So this must be a functor from C to D, which has certain properties. Yeah. Which has a certain, which has a certain structure, namely a bimodule structure. And if you reduce this bimodule structure, then you see you want to have here a bimodule, which is a functor from f from C to D, and I can describe by the bimodule property the functor uniquely by its image in D. So, and what we get in this way is a category where I can I have a bimodule property f and d. This here was G on the monoidal unit of C, tensor f of C. Now the bimodule property means that I can write this as 1 in C, tensor C, but this is also G of C tensor 1 in C, and I get in the end isomorphisms to f of C tensor D0. So what you get here is a bimodule will be described by an object D0 this is D0, this is an object in D, together with a way of permuting f of any object in C to the other side. If f would be the identity functor, then this is a very famous category. This is the Drinfeld center. So we are having a generalization of the Drinfeld center. That's the upshot. So let me define this category for which we get. So we get for a monoidal functor in C, we get the following thing. We have the notion of half braiding. So a half braiding on an object D0 in P. This is exactly a natural family of morphisms, of isomorphisms here, and it has to obey some coherence conditions. So this is actually as fits a braiding a hexagon condition, and then you introduce the category of all these objects with compatible morphisms, and this is a category which, in the case of the identity functor, is just the Drinfeld center. So you see we can introduce coefficients which are a natural generalization of this Drinfeld center. And if you want to see how this works out in this complex, then I should add here the following data. So our complex will now be written in the general case. So we have a functor and we have a pair of coefficients which are x and y in this generalized Drinfeld center. And now you see that we are going to add here to the left of x a line which is labeled by x, and I have to continue this line. So this will go now here. We have a morphism which goes from x tensor these objects, and here we have a y, and here I have to cross. This is exactly where I'm using the half braiding. Yeah. And for the y, that's a similar thing. And you can sit down and check from the hexagon and the properties of the coherence properties of a monoidal functor that this is again a differential. And that's how we did it originally, and it was reasonably painful. Yeah, but this is the complex we consider, and it puts us into a very nice situation because we are now getting close to the following adjunction. And this will be really what gives more structure to the problem. So we have this category here, Z of F. This is our generalization of the Drinfeld center. So we can put images under F on the other side. And I can forget this half braiding, and then this is just an object in D. And this functor has a left adjunct, which I denote by calligraphic F. And we should note a couple of things which are so this functor here is in our setting exact, and it is monoidal. And then this functor here is obviously not exact necessarily, but it is still opmonoidal. So we have an opmonoidal functor which is left exact. So left exact and opmonoidal. It is also very explicitly available, and we get on top of this by composing here this functor, we get a monad, and actually a bit more than a monad, because the monad comes from an opmonoidal functor. So this monad is called, is actually a Hopf monad. So, and we will be able to use now tools from Hopf algebra theory. That's the insight. And I should also mention that if I first go down and up, I get a comonad. And the comonad is, of course, important for building up bar complexes. Yes. So that's why it's quite nice to get into this setting. I mentioned that this functor here is pretty explicit. So let me mention how f looks like. F on B can be given by a coend. Now I'm using rigidity. And I take a coend here over C and C. So we know this functor very explicitly. And we do the following sample calculation. I want to take the simplest case and not use Davydov-Yetter here for the case where I have a functor, but I choose this functor to be the identity. Okay, so now I want to compute the co-chain groups, and these co-chain groups is something we want to compute together. So how do you compute natural transformations?
Sorry, is that the definition of the left edge point? Or what is the f of d? This
F of d is...
And that's how the left adjoint is defined.
That's how the left adjoint is defined as the left adjoint,
yeah,
but
yeah.
that's how it is explicitly given.
Okay.
So I want to show you that it's a very explicit object,
Yeah.
which we can use specific properties. But it depends very crucially on the fact that we are working with rigid categories.
Yeah.
And I don't know how to generalize this to the non-rigid case.
The existence or the formula?
The formula. So there is a generalization, there's a proposition. So Street proposes to work with a hypercomonad, but this looks to me like a frightening gadget to which I cannot give any deeper sense. But of course, if Street has an idea, we should take it seriously.
It's really the existence. Is this through CAN extensions, or how do you show the existence?
Well, I show the existence because I'm working in a specific setting of finite categories, and then you can show that certain coends exist because, for example, I have a projective generator and I can use the projective generator to realize it as a cone.
Okay.
And honestly, at this point, I'm a bit lazy because we could do this more generally if we go to admit int objects and so on. And these are things you guys would do immediately, but we wanted to go to the simplest setting. Yeah.
Thank you.
Okay. Yeah. So now let's do this calculation, and probably one of the most useful insights about n's is that you can write natural transformations in terms of n's over homes. Yeah. So I have here a functor which is tensoring n objects. So I'm writing the result of the functor, that's x1 to xn, and here I have x1 to xn. So I'm writing here the image of the functors, and I take a coend over xn. And now I transform this using rigidity. And what I'm going to do is the following one. I'm going to shift x1 to here, to this side. I can do this using rigidity. So I get xn, x1, the left dual tensor x1. Here it continues with x2. I take the x2 and take it over. x2 dual tensor x2. It continues in this way. Then you know that this is a limit, and the limit can travel inside. So I can also write here this into xn, and I've rewritten this expression. And here it turns out that this here is exactly the form of the comonad, which can be given in terms of an end. So really, this expression is Hom1, and then you take G. Well, there's a Fubini theorem for n's, so it's applying G n times 2. Well, and here between this, I could smuggle a monoidal unit, and you get this. And now you see already that this has the form of a bar And this is, of course, very nice because now we can identify Davydov-Yetter cohomology with something which is known since the 70s, probably, namely comonad cohomology, and we can open textbooks about this. Okay. So let me note. So Davydov-Yetter cohomology is a comonad cohomology, and that implies that we have bar complexes, and there's a whole lot of homological algebra redeveloped. So one knows what is a G projective object, what has fundamental lemmas, and all homological algebra you know from textbooks is available in this setting. What I want to do to finish this part is to show you how this gives a very simple conceptual proof of Ocneano rigidity. Because now we have something which is a Hopf monad, so morally it behaves like a Hopf algebra, and we can use comonad cohomology to get this into. By the way, since you take photos, you can have my lecture notes. They stand in, yeah, because I know that it's a bit hard to. So I can also. Can I send it to Arne? Yeah, then you can distribute it to those who are interested. Yeah. So I discovered a few nasty typos which I would like to eliminate first. Sorry. So, I was too lazy to carry my iPad with me to do this yesterday in the hotel. So, but let me give this conceptual proof of Ocneano rigidity. Ocneano was an operator algebraist, but quite a few of these categorical results had been discovered in this operator algebraic context. So let me write a couple of lemmata. So the first thing is that if this is a functor, the monoidal functor is between semi-simple categories, and semi-simple finite categories are also called fusion categories. So the point here is semi-simplicity. You can show that this Z of F is also semi-simple. How do you show this? This was defined, well, actually, the adjunction I have shown you is a monadic adjunction. So you can show that this is modules over this monad. When are the modules over Hopf algebra semi-simple? If you have a nice integral. You sit down and you will find a nice integral, a high integral, that things are semi-simple. Yeah, so that's the proof strategy. And it's not hard because we derive it from known properties for the integral of some other Hopf monad. So you could be completely lazy about this point. This is the second lemma is something which you have to prove. So maybe it's known in the literature, and U is faithful. Then you show that if our P in Z of F is projective, then it is also G projective. Recall we have a Hopf monad. So G of something is a free module. Direct sums in free modules are called G projective modules. And in this way, you show that projective implies G projective. And now the theorem we can prove with this, this is with Matthew Page and Jonas Haverkamp. This was part of a master thesis, is that if we are in this situation, so if we have semi-simple categories, then H and Davydov-Yetter of F, X, and Y is equal to 0 for n bigger than 0 and all coefficients. So this includes a whole bunch of rigidity statements for module categories, for gradings, and so on. Yeah, because we have reduced this. And I can tell you the proof. The first point is that since it is not known that cohomology on G projectives vanishes. This is a standard homological algebra argument in textbook style. Yeah. So the next thing is our functor here is a forgetful functor, so it is faithful. As a consequence, all projectives are G projectives, but this is semi-simple, so all objects are projectives. So all objects are G projective, so that's why the cohomology vanishes. This is a very conceptual reason for rigidity.
I'm trying to think of some examples of algebras or affine group schemes for which this will be semi-simple. Maybe some examples where the deformations won't all vanish. If you look at representations over such a Hopf algebra or over such a group scheme, because do you maybe know an easy example of one that has interesting deformations?
Yes, and I will say a few words about it, and then please ask the question again. No, and if you don't have enough time, ask the question after Violetta's defense.
I'm sorry.
Yeah, no, it's a good question. Here's the semi-simple situation. You don't expect anything. Yeah, so in the sense, this is a rigidity result. Okay. Now I'm sketching you how you can proceed, and then we will have. So we want to relate this to also some very well-known theory. There is relative homological algebra. If you go to MacLean's book, 50 years old, there's a whole chapter about it, so nothing new or inventive about this, the method. So in this case, he considers two abelian categories. Then there is a functor here which is additive and faithful, and it should have an adjoint. And given this setup here, this is something he calls a resolvent pair. There is a small observation which I'm not going to prove. It's not in MacLean's book. Such resolvent pairs, these adjunctions are always monadic. Yeah, so probably it's known to the experts. So this is a monadic adjunction. So now what we can prove is, this is a theorem now with Fage-Danoni-Long, is that if the functor f here, monoidal functor through D, is, in our paper, it's written exact. But we have improved it to saying that it is right exact. Yeah. So then Davydov-Yetter cohomology for f and coefficients f and w is relative cohomology. I'm writing here ZF, D, but really the whole adjunction data enter in the definition of V and W. And now we have long exact sequences. Now I can compute examples where I can show that this is non-zero. Yeah, I can do even so. I have long exact sequences. That's one thing, and I can. The other thing is also I have a Yoneda product of cocycles. So if I want to get explicit cocycles which correspond to deformations, I can get even the cocycles explicitly. Yeah, so that's another advantage. And now what you can do is, for example, you can do, well, let me first give a proposition. So, for example, you can show that Davydov-Yetter cohomology for any functor in characteristics 0. First, Davydov-Yetter cohomology vanishes. And that's a very short proof. If you analyze it now as if you analyze it now in and here for sorry, I'm getting a bit too fast. Sorry. Yeah, if you analyze the first relative x and you analyze this here, this is contained in the standard relative x, but it's a textbook result that this vanishes. Yeah, so you get vanishing results, and you get very explicit formulae for Davydov-Yetter cohomologies, including formulae where you get non-zeros. So we get them from small quantum groups. Yeah, so finite dimensional Hopf algebras. And the way to do this is as follows. You take the monoidal unit in your category set of F. Let's assume that this is the case for the Trinfeld center. You're choosing a relative projective resolution. And then you can find the kernel of the surjection of P1 to 1. And let's denote this by K. This is some representation theoretic calculation. Yeah. And then you can show that the dimension of, by some long exact sequence argument, that the dimension of Davydov-Yetter is the dimension of, let's take the identity here, the dimension from the kernel to M in Z of C plus minus the dimension of Z of C from F to M, from P to M plus some other term. So, and here is M is also something very explicit. M is you take the monoidal unit and you tensor it with the dual of this object K, of this kernel, and you take it to the power n-1. So purely representation theoretic. And you can compute it, and Mathieu Fetch, to whom I should give a lot of credit, he computed it partly by hand, partly using GAP on a computer. Yeah, so that's very explicit, and I want to conclude that we stay in time. I promise to stay in time. I should say, give one more comment. The annoying thing here is at this moment that we have here a category Z of F, and I would have to compute a monoidal unit, compute a projective resolution all the time. So for every F, new work. So this is something we can now avoid, and let me sketch how we avoid it, because this is a result which makes many more things computable. Well, what do? We have here our adjunction Z of F. It's a forgetful functor to D, so that's UF. It has an adjoint, and here I have C, and here we have the central monad, which is the same thing for the identity functor, and that's something where a lot is known in the, at least in the case of finite tensor categories. So here's our functor F. Now, it is not difficult to lift this functor here, because we need to lift a braiding here to a braiding which involves F. Yeah? So we lift this functor, and then you can show that this is a morphism of adjunctions. By a morphism of adjunctions, I mean that going down here and going up is the same as going here, and that implies that it goes in the other way around. There's a small thing, it's not literally a morphism of adjunctions in the sense of MacLane, because these things, these defunctors commute only up to some natural isomorphism, which we have to control. Yeah, so but this it's not a nuisance. It's technically a nuisance, but it's very natural. And now you can show that this preserves relative projective resolutions. So now we are in business for homological algebra. That's the next idea. And then we assume now that F has a right adjoint. Yeah? So then there's a theorem how to lift in such a situation a right adjoints. That's very old, I think from the 70s. So let me write this here. That's R, and then we lift it to some R twin. And then the statement here is, and this is a statement I'm really very happy about, is that Davydov-Yetter for F is, because we can relate the relative projective resolutions, is Davydov-Yetter for the identity functor. So we compute only here using the standard case. Coefficients are, one is even triggered, so we can do a projective resolution of this coefficient. And here we have this right dual applied to the monoidal unit. Of course, the monoidal unit here. So we can reduce Davydov-Yetter for F by using such an adjunction theorem to Davydov-Yetter for a very well-controlled adjunction by using this coefficient. And now comes the thing which intrigues me very much, and that's what I want to conclude the thing on. If you see, this is by definition an object in Z of C. If you have a modular tensor category, modular means more or less that C is braided, and it is braided in such a way that Trinfeld center has two copies of F. I'm cheating a bit because here I have one with this braiding and one with the other braiding. Yeah. So what we get is here an object in here. This object has a conformal field theory interpretation. And this is the object which describes bulk fields in conformal field theories. So we hope that in this way we can understand why physicists reform conformal field theories using bulk fields. But it comes from very clear and very standard deformation theory. And I cannot turn this into a rigorous statement at the moment because we have these additional qualifiers of the categories which we have to take into account. They're like pivotal and this stuff. But the technology has to be extended. That's one word for the outlook. Second word for the outlook is we keep the categories fixed here. We keep the functors fixed. We're just deforming the linear structure. It's, of course, very interesting to do more. That's why I find the techniques in the thesis we are going to learn more about in half an hour very interesting and potentially relevant. And of course, one day our dream is to have also some computational tools for this that we can actually compute also. But there's time for challenges. Thank you very much.